Hello guys and welcome to this channel. My name is Roman Narvaez. I am a civil engineer with a specialization in structural engineering. I am sending this workshop from the city Gothenburg city here in Scandinavia, and today we are going to explore how to compare steel beam with versus timber beam. That's the case here on the screen, and we are going to use only, in this case we are only focusing in the moment. In other workshop we are going to go through what is about deflections. So to begin this, I have here construction here. I'm not going to show you what I mean. For example, we take the system line in 15. The exploration will be, for example, we have some steel beams, and we have the other ones which are the timber beams. So to go inside this calculation, let's go to the my iPad, and here is the iPad, and we are going to use the application concepts to show you. We open concepts, a new drawing. That is the application. Sorry, I need to put another thing here. Right. So we are going to separate the canvas here. That way, I suppose that's okay. So we divide this into maybe we need to make it more exactly that. So steel here. In this part we're going to put our stuff about steel, and the other timber. So the first we are going to draw, we take the case a simple supported beam. So we have to kind of loads here. We are going to move a little. So the first load here will be the self-weight of the beam. Which is the self-weight. And a distributed load that we are going to use. Q distributed load. We have a span here, L equal 5 meters. The distributed load in the both case it could be 10 kilonewtons divided 5 meters. And in the case of the set weight for the steel, it will be the one, for the timber another one. So we take a copy for this sketch here, we copy this, and we move to the other side. So I think it's quite okay there. So for the we make an assumption at the beginning that we have the bin. It would be, for example, it could be a bin that is, suppose that you have a bin like that. We can call this HEA, and we need at the beginning some guess, for example 120, and the set weight for this is around 199 kilonewtons divided by meter. So afterwards we need to apply Eurocode safety factors for set weight for a variable load. So Eurocode here, and we say it for, in this case, at Q ds equal 1 dot for the set weight of the steel plus 1.5 Q distributed load. We put the values here, and we get 1.2, 199 plus 1.5 distributed load 10 kilonewtons meters. This value gives us 15 to 39 kilonewtons meter. So we have that, and as we see on the picture here, the diagram here, we have a simple support to bin. In that case, we can apply a moment for the steel, which is QDS, the span width, to the 2 to the square, divided by 8. This is for a simple support to bin. So we put here the values, and we have 15.239 kilonewtons meter. The span width 5 meters to the 2 and divided by 8, and if we calculate this value, we get 47,621 kilonewtons meter. Very good. As you remember, we are going to apply this formula, which is bending stress. The theory is quite a lot. I can go through this in another workshop, but I can show you very fast. This one is coming, this theory, from the curvature of a beam. Normal stresses of a beam. There is 3 aspects that are involved in this demonstration of this: the geometry, the Hooke's law, and the static equilibrium. Give us that formula. Right. So we apply that formula, and we put here that the stress for the steel equals to the moment that we get cotton above, and this is divided by what we call this the second moment of inertia for the steel. So from here we are looking for the second moment of inertia because we have this moment and the strength of the material, the steel, we have here, which is and is equal to Fyt. So what we are talking about is that we are looking for this stress versus the strain. We call the yield strength. For our purpose, we need to look at for the steel. We are looking for a construction steel 355 and a safety factor for the material 1. It means that we are going to use, of course, Fyt 355 megapascal. So in that case, we replace this value on the second moment of inertia formula, and we get the first the moment and maybe we can express this in newtons meter. In the case 355 10 to the 6, and this is Newton square meters. This gives us that our second moment of inertia is equal to 134 10 to the 3 in millimeters to the 3. With this value we need to go on some table, and I have a table here so we can look at that table. Construction table. At the beginning we took the set weight of HEA 120, and we will see the elastic second moment of inertia is 106, and here's the units, and of course we are a bit low in our guessing, but we can take HEA 140. So we choose EHI 140, and this gives us a second moment of inertia in the zone, which is the elastic zone here, and give us 155. Good. So we have in this case for the steel, we have got what profile we can use, and we are going to make some similar calculations for the timber. So okay, we can choose this force this to. We copy this. So, and we are talking about, for example, a profile. I am using a profile like this, for example. B, I guess only a B. 70 millimeters. And H, it could be something like 220 millimeters. So in this case, we know that this cell weight is not the same. So this is not the same. And we change that. We call timber for the timber. Yes. Which is the cell weight for this? Yes. The cell weight for this we need to calculate, and for that, so how we can do that way. So the area, for example, we need to take the density of the timber. The density of the timber equals to, from some table like this table here. We will see if we have a table here or here. Construction table. Here we have the density of, we are going to choose a C24, and for that purpose we got density 350. So 350. Okay, density is in newtons, it will be 35 kilonewtons meters to the 3, and we need the area as well. The area here from this profile BH, it will be 70 by 22, and this is square millimeters. So the area that we get here is 0.015 square meters. Okay, with that we can take, for example, the QT for the set weight, which is of course the density by the area, and this gives us, if you put the values over there, we get 0.054 kilonewtons divided by meters, and we put this on the formula that we got. And of course we must change these things here. Here we are talking about timber. What's timber? That's timber, 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 timber. Of course that is incorrect. So we get in our calculations QT equal V. This equal be 15.065 kilonewtons meter. And we replace these values on the moment for a simple supported beam, and we get here 47 077 kilonewtons meters. You compare the moment. In the other case, we have another moment which is bigger in the steel, 47.62. And in the case of the timber, we have 47.077. So it's lesser than the steel, of course. Okay, but we need to take the second moment of inertia here. We are going to choose a C material, C24, which means that we have strange equal to 24 megapascal, and we need to apply this in this case for the strange in the ultimate limit state. This is a definition, and we can find this in our code. And for the timber, we need a safety factor for the structural timber 1.3, and we need to use as well a strange modification factor Q mode for structural timber, and this have to do with a low duration class, maybe 0.60 or 0.50. So in that case, we are going to put here our formulas for the strength of the material, the Q mode, F characteristic, and divided by the safety factor for the material. As I told you, we use a Q mode equal to 0.6, and safety factor for the material timber structural 1.3, and this gives us strength for the material. If we put the values here, 11.076 megapascal. Right. Of course, we apply this formula that we have here, but for the timber, that is the normal stresses, or the stresses, sorry. So yeah. So for the timber, the second moment of inertia will be like m dt yes, and that it will be a minute, please. T, yes, of course. I need to make a little verification here. So yes. Alright, that the FD that we have calculated here, we put the factors here, we have the moment, we have the the strength of the material, and this gives us a value of 4.25 by 10 to the 6 millimeters to the 3. So and yes. Okay, in this case now we get the value of this beam, and we need to check this with some kind of table, and we can look at, for example, for this profile here, the profile here, which second moment of inertia you got. We go into this table here, and we are going to look here. For example, we have it in this column, the second moment of inertia for 70, the width, and the height 22, 20, and this is 564.7. So we can put this on our we get value, a max value for this from the table, 564 by 10 to the 3. You could calculate this with the resistance of the material as well, like in the formula, very simple. The width to by the height to the 2 divided by 6, and you get the same result. So you get the relation between the what we need, the second moment of inertia divided by the profile, what we need, but divided by 1 of this profile, we get that we need 7.5 profiles. So you could say that is 8 Vmax, and that's not acceptable. You can think that you are going to have this here. If you copy this, I put so. We need to put together 8 beams like that, 8 profiles like that, and that's not a good solution. We can take 2 here together, 4, and finally 8. As you see, to get that second moment of inertia, it will be unpractical. You need to put together some kind of hoop in this way, for example. And that is not acceptable. In this case, we will see that you can see that the steel is very strong, and for the in focus of the moment. So in the next workshop, we are going to look at about the deformation, because the deformation, as you see in this, I'm going to show you the material here. Yes. So in the deformation, there's a big issue using, for example, the E module for the steel and the timber. You see, is very quite different. The numbers are quite different. So, but that's another issue for the next workshop, for the deformation between steel and timber. So I hope that you get more knowledge about structural engineering. Have a good time.